version of ultramast, so BXA. Is extremely powerful method, and it is going to be interactive. So break out your laptops, go to that tutorial setup and start downloading and making sure that it actually works on your laptop. It works on both XVIII and Sherpa. And with that, let me hand it over to Johannes Buchner and Peter Boorman, who are actually where are you? And Max Planck?
Yes, Max Planck.
Who are here traveling from New York just for us. So thank you both, and take it away.
All right, thank you very much, Vinay. Thanks for accommodating our slot at this time. And I think switch to our slides.
Let me start there.
I think you have to actually hold the slides from here and switch as well.
And also, it's been recording all this time. Okay,
that's good. Yeah. Okay, does that work? Okay. Is it good? I think it might be as good as it gets. Yeah. All right. Yeah, my name is Johannes Buchner. And I'm Peter Boorman. Yes, and today we're just going to do like a brief introduction to some of the background for sort of statistical aspects to X-ray spectral analysis, but as applied in BXA. And so yeah, a bit of an overview of what BXA is and what's sort of covered in the tutorial with the link that Vinay just mentioned. Okay, so yes, for anyone interested, we're going to go over a few slides and things, but the actual content of this workshop is quite similar to a few previous workshops that we've done. And if you're interested in any of those, we've given a few like lectures and different workshops, and all of that material is also covered in these, probably in a bit more depth as well. So yeah, just Google any of these if you're interested in like finding out more details in general. And yes, I should also say that all of the content of the tutorial in terms of the exercises are all covered in a chapter that Johannes and I wrote for the Handbook of X-ray and Gamma Ray Astrophysics, and that sort of breaks down all of these concepts with a series of sort of interactive exercises, and the exercises are more or less exactly based on the tutorial itself. Okay. So yes, in terms of the textbook itself, it gives more of an introductory level before going into exclusively BXA. So the broad sort of like concept that's covered in the initial parts of the textbook chapter is kind of encompassed in this figure here, trying to sort of summarize the typical story of an X-ray photon that's detected for a typical CCD level X-ray spectrum. So what you can see here is in the top left, some sort of interesting astrophysical source, whether it be the X-ray corona around some kind of accreting compact object, as depicted here, or whatever it might be. It gives you some interesting astrophysical spectrum, which is the fundamental thing that we're interested in, right? The shape and the parameters specifically that describe this model, but we don't see the astrophysics, right? We actually see a linear, a convolution with the response matrix, and also the ARF as well, in terms of converting that into detected channels. And then from there, we actually see a Poisson realization of those counts that are simulated from a Poisson realization. And so the whole idea is fundamentally how to go from this Poisson realization of the astrophysics to then go back to inferring what we can about the astrophysics as well. And so in terms of that sort of story, that is covered in the first area I'm saying here as X-ray astronomy, where we sort of go over this linear instrument model concept, as well as the different types of likelihoods and statistics you can use. So whether it be Poisson statistics with CSTAT or Gaussian statistics with chi-squared. We'll discuss a little bit later in terms of background treatments, like the different typical background models that are assumed to simultaneously fit a source plus background spectrum and a background spectrum, how that's typically treated in XVIII or Sherpa or other spectral fitting tools, and kind of a convenience feature that's included in BXA to have sort of flexible background models that can be fit simultaneously to use and to take advantage of like true CSTAT statistics and likelihoods. In terms of, we then sort of cover frequentist statistics, so including how confidence intervals are calibrated. So this idea that if you assume that you observe the ground truth, then 68% of the time, 1 sigma of the uncertainty regions will cover that truth, and how that's sort of calibrated typically. More about sort of model comparison, so how to calibrate false positive and false negative rates when you're using a particular threshold, whether it be a more conventional likelihood ratio or later on things like the Bayes factor, in terms of trying to select one model over another, how often you would get that selection wrong, and you can do that by calibrating with simulations. And then also, just as a sort of almost reminder that MCMC, some implementations of MCMC can sometimes almost hide or mask the fact that a prior is assumed. So for example, there are some implementations, for example, in XVIII, where it doesn't necessarily explicitly state that there is a prior, because you can start from a single point in parameter space, but fundamentally under the hood, any MCMC analysis does assume a prior as its backbone, right? Which is more of a Bayesian technique. Now, in terms of the actual tutorial itself, it's more or less focused around this idea of a Bayesian workflow, right? And so it covers the typical ordering for a Bayesian workflow. That in reality, this is actually more of a closed loop, but it kind of starts by designing priors, right? And what that actually means. So typically these priors, they're not based on what you expect the source to be doing, but rather your actual prior knowledge, right? So if you know nothing about a source and then you look at it, you can be fairly confident that it's not going to be, for example, brighter than the sun. It's not going to be, if you know that you detect it, it's not going to be faint enough that your model shouldn't predict a flux that would be so faint that the instrument can't detect it, things like this, right? So that can set like an initial prior. If you have prior information about the system, you can also fold that into your prior as well. And then different Monte Carlo algorithms whether you use MCMC, so things like MC or slice sampling, Hamiltonian Monte Carlo, if you have knowledge of the gradient of your likelihood space, a bit more extra information, just so that each step is a bit more valuable than a typical sort of MCMC analysis where you don't have information of the gradient. And then also, so for BXA specifically, which is more based on this idea of nested sampling, so where you sample from the global parameter space initially, and then continually remove points until you have a more restricted posterior. And Johannes is going to talk a bit more about the theory for that in a few slides' time. But then the idea is to go to then derive posterior parameter distributions, so the sort of probability of your data given the model, and the idea that by using Bayesian model comparison, so with Bayes factors, it's more of a built-in Occam's razor, because Bayes factors typically have the ability to say when there's not enough information in your fit to be able to decide between two models, which is a tricky thing for other model comparison techniques. We also, in the textbook and in the exercises a bit, we cover the frequentist properties of Bayesian analysis, and this idea of experiment design, where in reality, this whole process would then be a continual loop where you might redesign a new experiment to get more data to try and constrain a particular parameter, or you might even do this loop with the same data, update your priors, and continue in that way. And so this plot here kind of shows this process, where on the left, you're doing prior predictive checks, right? So all of these model lines are purely thrown on the plot to check that the prior is kind of making sense for the observed data that you have. Then you derive a posterior, and from that, you have your marginal and your conditional parameter posterior distributions. So the conditional ones are here. So in this case, for a power law, it would be the conditional probability of your normalization, and your photon index, right? And then your marginalized histograms show your probability distribution of those, where they're lovely and monomodal in this case. And then some sort of verification of the quality of the fit. So in this case, I'm showing cumulative residuals, so quantile difference plots, where this can be a bit more beneficial when you have very low count systems, because then you don't have to do any binning, as you can see here. And so in the orange, this is showing the cumulative difference in the data minus the model that's been normalized to the total number of counts, and where, because you're relying on the cumulative data, you can then quite arbitrarily simulate where you would expect if the model was perfect, which is this gray oval. And so you can statistically start to say that a deviation of the model from the data is significant when your orange, in this case, orange line, deviates from the model. And in this case, it's just because we're using a power law for a model where you have significant absorption and you have a strong ion line, right? And so that's why it looks like there's a big deviation centering at this point, which is something that might, for low enough counts, be difficult to visually see for a conventional residual. Okay, and so yes, for the tutorial itself, and I'll bring this link back up, but the tutorial, as Vinay said, is just for this link that we'll be covering today. Okay, and then
all right,
over to Jan.
Yeah, so I will continue with sort of Bayesian inference. You probably have seen this formula before, so I will not spend a huge amount of time on it, but we have this prior, we have the likelihood function, which is our CStat Poisson probability, essentially. And what we're doing in Bayesian inference is to compute the product of those two, and that's proportional to the posterior. So what we're doing is at each point in the parameter space, we're computing the prior density, which might be flat, times how probable this point is at explaining the data observed. So that's the Poisson probability. And you can do this over the entire parameter space. You could do a grid, for example. And that would give you these contours that you can then project in or sum up with the marginal distributions. But you can also integrate over this entire parameter space. That's the normalization factor, and that's this quantity there at the bottom, and that's called the Bayesian evidence. And that's a very useful quantity because it tells you sort of the average over this parameter space, the probability, the prior average likelihood. And that's very useful quantity for comparing models. And I'm gonna talk now a little bit about how that's computed and how, so if you have more than 2 parameters, a grid will not do, how you can actually compute this integral and how you can use it then to compare 2 models. And that's sort of one of the main motivations of why you might want to use BXA. So, right, so let's say you have one model here illustrated with one parameter space and another model which has a completely different parameter space. And what we're doing then is we compute the likelihood at each point. We take the sum or the average, and we do the same here, and then we compare 2 parameter spaces by taking the ratio of these integrals, okay? And you see also some important aspects here. You have to choose how many points you put in this parameter space versus this parameter space. So this is the a priori probability of one model over the other. You might choose that they are equally probable, but that's the prior choice. This is the model prior. And then you can also see it does matter how you space this parameter space and how you put the gridding. And that's a parameter prior, how you choose some regions of the parameter space to be more probable or more relevant for your integral over others. So both priors of the parameters and of the models are important. But now let's look at what that does to compute this ratio of evidences. So let's say model 1 is a very flexible model, okay? So let's say you have some data points. This is generally speaking about Bayesian inference. Let's say you have some data points and you have one model that's extremely flexible. It can make all kinds of shapes, okay? So you will find a tiny region in this parameter space that exactly fits your data. Okay. So a very, very small region will have very high likelihood. And as soon as you move away a little bit, because this model is so flexible, it will do something completely different that doesn't describe your data. And because we're averaging here over the parameter space, a small region of this integral downweights the maximum likelihood here. Whereas here, we might have an inflexible model, which sort of moderately describes your data, but over a larger fraction of this parameter space because it doesn't have to move that much. Okay, and so this integration, this Bayesian evidence, what it does is it punishes flexible models. It has this built-in Occam's razor that says not only does a good model have to predict the data at hand, but it's downweighting data that you could have seen but are not realized in your observations. And it's really about the prediction diversity, prediction in the data, not specifically the number of parameters. So you can imagine if you add a parameter that doesn't do anything, you would get actually the same integral. Right, and so Bayesian model comparison, you take the ratio of those two integrals, that's the Bayes factor. You multiply this by the prior odds, so how a priori, how probable one model is over another, and you get posterior odds. So you can interpret this as model 1 is this much more probable than model 2. I have a few more sentences here. Well, this is generalization to n models, so you can also do that with very easy formulas. I have a few more slides here on different types of model comparison. Let me very briefly mention that. So there are also different styles of doing model comparison. So for example, if you just have the model but not an alternative, so you're testing the model in isolation, then you wouldn't use Bayesian model comparison because you're not comparing, you're just checking the model in isolation, and there you could do realizations of the data like Peter was just explaining and checking whether they have similar, whether they look similar to the data. But here, when you're comparing, you could also ask, are you comparing two physical models or just you try to summarize the data with some empirical formula like a polynomial or something, then you might go to something more in the direction of machine learning where you only care about prediction quality. Okay, so for example, with cross-validation or with the information criterion, whether this model is sufficiently complex to summarize the data. And then, yeah, you might also subdivide in whether you just have one model, which is a subcomponent of another model, then you could do something else like parameter estimation. But in both cases, you can do Bayesian model comparison. So it's a very general framework because you can apply it in many situations. Okay, this is just a slide again about different algorithms, and I will now focus on nested sampling, how you can actually efficiently compute the integral over a high-dimensional parameter space, be tens of parameters, right? And so now I'm gonna explain how nested sampling works. So just as a contrast, here is how you could divide up a parameter space into a grid, like I was saying before. And the integral on the top there is then the sum of the values at each grid point times the size of each grid cell, right? This would be a Riemannian integration. An alternative, and the contours here, the colors are giving an example of what a probability distribution would look like, the posterior. But just imagine any shape there. Just imagine any shape there, and what I'm going to describe doesn't depend on the very nice circles. So the alternative, and this is what this sampling does, is to do this kind of integration where you say, well, I'm going to try to find regions of equal height, right? And then I'm going to sum the height times how much shrinkage there is between different height layers, right? So we're trying to find these sort of almost the contours, and integrate up this pyramid, if you will. And that's Lebesgue integration. Right. So our goal is we have our likelihood, we have our prior space. We try to find different levels, and we have to know how much smaller the next level is compared to the previous layer, and then we can do this integration. Okay, and so how does nested sampling do it? Well, so we have a population of live points. We throw them into the prior space, and they're randomly distributed into the prior space. And some might land far out, have very low likelihood, and some might lie further in. And then what we're doing is we remove the one with the lowest likelihood. Just add a few here. Sorry. Then we remove the point with the worst fit, the one with the lowest likelihood, and we're gonna sample a new point from the entire prior, but we're not gonna accept fits that are worse. Okay. So what we're doing then is we rejuvenate this live point population, but we are not considering this dark purple region anymore. We've excluded some space. And in this step, the key is that we can know how much space we have now excluded. And the fraction of the space is statistically 1 over the number of points. And so in each nested sampling iterations, we're going to remove the worst fit and never consider any point sampled from the prior below that likelihood threshold. And in each of these steps, we are discarding and never considering anymore 1 over the number of live points as a fraction of the volume. Okay, and so we're keeping track of how much this volume shrinks. We're restricting to higher and higher fit qualities, higher and higher likelihoods. And so the sampling process has a live point population that walks up to the peak until it reaches a very tiny fraction of this parameter space, and the integration is done because the product of the likelihood times the size of the volume is going to get smaller and smaller and smaller as you keep adding. And so as you build this up, what this looks like is the first slab, you remove this much of the prior space, and this is the height sampled here. You know the fit likelihood, and you keep summing as you take out live points and put new ones in. So you build up this integral that way. The theory of nested sampling has the whole literature attached to it. I wrote a review in 23. You can find a lot of background on it, including proofs that this converges, diagnostics, variations of the algorithm. Many people have worked on how to efficiently implement this, and multinest and ultranest are packages that do this. In particular, how you sample a new point with this restriction that you don't allow the fit to get worse in a fair way, sampling from the prior. This is this whole area, and I will not spend a lot of time on that. Good, then we go over to the interactive session. So I think the idea is that you have to now do work. And so you please go through the tutorial, and we'll walk around and be available for when you get stuck.
Well, that's
And
people have any questions, can they?
right.